Hello everyone, and welcome back to a new episode of SHENZHEN I. Not much to say here. Let's just dive in and see what our next assignment is. Undocumented instruction. I was chatting with a mate at the pub, and it comes to light these SHENZHEN microcontrollers we use everywhere have a secret instruction that isn't in any of the documentation. Takes the format of Gen... Get out of here, mouse cursor. Gen P and two, registers or constants. And it generates a pulse on a simple I/O pin. The signal switches on and then off for however many time units you want using the last two things. Gen PXY is the same as moving 100 for and then sleeping for X, then moving 0 and sleeping for Y. Huh. The at conditional? What? Don't mess with me, game. What? Alright. Oh, I guess... I didn't see the scroll bar, and his thing lined up so nicely with the bottom of the screen that I thought that was just like, yeah, you just gotta live with it, the at conditional. Go figure it out. But alright, hopefully it'll tell us. The what? Many instructions are not translated yet. Putting an at the beginning of an instruction causes it to execute only once. I see. So that's, if you're familiar with C, it's like a static variable in your function. Or I guess that's very similar to a static in, in Java. Or, many other languages have something like that. Okay, so we learned some new tools. And that's interesting because it means we could go back to some of these earlier ones and solve them much more efficiently, right? So let's just, for example, go back to our camera thing and we'll make a new design. I want to just wipe all this garbage out and look at our verifier. And in here, we will just say, what's it called? Pulse? Pulse on P0, 6 and 6? Is that correct? Yeah, it didn't light up any errors, so apparently you can just do that. No. It's not... I already forgot what it's called. Gen. It's called Gen. And we can do the same with this guy, right? We'll just... It generates on and then off, or off and then on? It generates the on first. Okay, so we can't quite do that. Oh, I see. And how convenient that the this very first one we went back to do, which we said, oh, we can use the gen for. You can't actually use gen for it unless you also, ta-da, use the fancy little at thing that they have, which is we can sleep for 6. Because we need the on first, and then the off. Or we need the off and then the on, and gen goes the wrong way around. So we have to start with a sleep that skips over the boring part and then gets us into the part where we can generate some pulses. So let's do the same here. Sleep for 4, I believe it was, and then gen on P0 for 2 and 1, and then gen on P0 for 1 and 4? I think that's it. Yeah, nice. So how is that for power usage, actually? Stop. So those sleeps, of course, take some power, or take like 1 power each. But then that whole gen just takes 1 power. I think? Gosh, I can't figure that out. So each of these sleeps took 1 power. And now we're gonna do something here, which for some reason is costing us 2 power? I'm not quite sure why that is. I see. So it's basically making us pay for the... We don't just spend 1 power for that instruction, we spend 4, because it's equivalent to move, sleep, move, sleep. So for a... So, and additionally, we're paying for the extra sleep at the beginning? We're paying like an extra power to get ourselves into the right phase when we don't necessarily have to. So I think this is actually slightly increasing our power consumption, but not by very much. And it's saving us something that we don't really need. So how is this? It's power of 58. And if I return to my email here and load up design 1, how was it doing in terms of power? Well, look how much longer this is though, huh? Power of, well, 58-ish. Okay, so we didn't actually gain or lose anything here, right? Because we're only paying for the instruction as far into it as we get. So it's the same power-wise, but it saves us some instructions, which will make it easier to squeeze more stuff into a cramped chip, hopefully. So for something like this light up signs, we might be able to save actual... well... maybe not, huh? I wonder, though, if if we could somehow use this multiplexer guy as a source of extra I/O ports, and just have 1 controller chip for all 3 of these. I bet we could. That would be interesting. Yeah. So let's load up another design. Also, did I end up doing this right? So I watched later Scott Manley's video of this, and he noticed something that wasn't obvious to me. Is that, so remember we have these 3 sort of related inputs here, and we kind of needed 1 on one chip and 2 on another chip, because like we have 2 outputs on any given chip. And so I was like, well, you know, I just couldn't squeeze everything I needed to do onto one of these baby chips. What Scott pointed out is that the number of lines of code that it takes to handle a signal is not a constant. It varies with how complicated the signal is. Drink 0 and drink 2 are simpler signals. They only have 2 transitions each. Whereas this guy has 4 transitions. And so what we should have done, if we wanted to conserve, to spend less on chips, is have 0 and 2 be controlled by a single small guy, and then have 1 be by itself on a small guy. Then we wouldn't have needed any big ones. Okay, very exciting. But what we wanted to do here, or what I wanted to do, and who cares what you guys want, right? Is to see if we can use this to improve our solution at all. And I think the answer will be yes. So let's start by wiring up this click thing as usual, just like we did before. Nothing too fancy going on here. Which one needs to be high first? Let's just move ACK to P1, not move ACK to P0. Confirm that that is indeed. Oh, let's sleep, huh? What do you guys say? And I don't think we can improve this at all with a pulse instruction. I think this is as good as it's going to be, because we're sending out two different pulses. We need to be sending them both at once. We can't spend 2 cycles on any of these things. Okay, fine. So yeah, that's working great. Very good. Now, what I want to do is have this guy, and we'll have another. This little chip here is going to be the guy controlling it. Oops. I keep just barely missing. In a fairly straightforward way, and we will just wire each of these up like so. And I don't know why, but I think it's just more aesthetically pleasing to go in the center there. And we will just decide whether to send a 1, a 100, or a 10 based on which of these 3 should be on. And then this thing will take care of mapping that into the 3, demuxing it, I guess, into the 3 outputs. So the first question is, well, I mean, there's not much, there's only one question, right? How many transitions do we need to do? 1, 2, 3, 4 in every cycle? Well, actually, we start with this high, so let's make our end when this goes high again. This is high, so call that a single transition. Then this is a second, third, fourth. Yeah, I think we can fit all that onto a single chip. So we're just going to, let's see, drink 0 is the one here, which is the lowest order bit. So let's move a 1 to X1 and sleep for 6. And let's just test that before we get into things. Great, so we turned on drink 0 just like we wanted. And then we'll move 10 into X1. I'm trying to see if there's a way we can use a pulse here somehow. What happens if you use a 0 in your pulse? Can you use that to just combine a single move and a sleep instead of 2 moves and 2 sleeps? What is it? Gen X1. We want to start with a 1 for... Oh no, we can't do that because this only sends hundreds, and we don't want to send 100. Okay. Okay, move 10 to X1 and sleep for 1. Move 100 to X1 and sleep for 2. Move 10 to X1 and sleep for 1. And we're now back at the beginning of the cycle, right? Yeah, look at that. Cool. So we were able to use this new part to improve and get a solution we could not possibly have done before. Right? We're in this area. Before, I think we were here, right? Because we had to use a 5 and 2 3s. Yeah, that's around here somewhere. And it would not have been possible to use a 5, a 3, and a 1 without using this new advanced alien technology. Cool. That's neat. On the one, well, let's see. We don't really have time to start a new puzzle right now, but we can certainly look at ways to improve existing puzzles, maybe. Can we do anything with this rubbish audio thing? I don't think so, because there weren't any pulses at all. It was just a direct transformation of the input to the output each step. This we could maybe improve a little, although not very interestingly. Oh, and maybe not even then, huh? Well, yeah. I guess we could just erase all of this. Well, not erase it all, but if it is 100 at some point, then we will just gen to P1, 1, and 1. So let's turn it off, on for a signal, then off for a signal. Is there any way something weird could happen? Yes. What if someone turned it on for just a single cycle? No. Because they have to... I was imagining, what if they turn it on just as our pulse is heading to off? We should therefore cancel going off and instead stay on. But they can't do that because our inputs only come to us one discrete time unit at a time. Yeah, okay, so this should be fine, right? Nope, wrong. Oh, whoops, needs a plus. All right, try again. Okay, and otherwise, sleep for 1. There we go. So that's okay. We're sort of getting the hang of our new powers. And we improved our power usage somehow? I guess because instead of using not... Oh, yeah. So while the buzzer is on, we're saving power by not checking whether the button is pressed. If we're on our way down off of a... here, I'll show you. If we're at like this state here, where we've just finished being on for a time unit, and we're headed back down, we should go down whether or not the button is pressed. So we don't have to waste power on reading that. And we're also not doing the sort of two-step process of not followed by move the accumulator. We're just move 0, move 100, move 0, move 100, with the appropriate sleeves thrown in, of course. The version with not was taking up fewer instructions, but more actual power, because each instruction was executed more times. I'm so curious. Show me the profiler. How does this... Yeah, look at that. We're spending all of our time in Gen. Good news. That's sort of the core feature of our product, really. Cool. Alright, back to the email inbox. Do we have any... Whoops. Go back. Do we have any others that are like going to be great? Great improvements? The drinking game score thing doesn't seem like we can really improve that at all with our new powers. Maybe we could improve it because we wrote it badly, but not because we got new parts and new instructions. Huh. These point and foul things seem awfully complicated. I guess it's because we're basically like implementing a latch. Yeah, you know what? I bet we could do this better. So what we're sort of storing in our accumulator is wait, what? Oh, I see. Can we somehow do a better job of detecting a state transition than this? And it sort of seems to me like, yes, we can test whether whether what is on P0 is the same as what is in our accumulator, rather than like testing it for 100 and then comparing it to the accumulator or whatever else. Just test whether it's different from what's in the accumulator. And then move the value into the accumulator unconditionally? I guess unconditionally, sure. And then based on whether the new value is... and then if the new value that we moved was equal to 100, then we'll send a 0 to the scorekeeper app. That certainly seems simpler. Can we do better? I'm thinking in particular of using this demuxer thing again somehow to take these guys out of the equation completely and just replace them with this guy reading the XBus demuxer. Or maybe it's a muxer, I don't know. And then the problem is he has to store quite a lot of state, I think, locally. He would have to store both the total current score and the state of which button is being pressed. So he would have to become a large chip. And then every time he reads a value... Do we have any cases where one of the inputs goes low and in the same cycle another one goes high? I don't see any. So we could maybe just yeah, let's let's try another design here. First, I want to do the sort of simplified one with the same layout as before, but with simpler chips. We're going to take that in there, and I guess these guys cost the same amount. Doesn't matter which one you use, I guess. Actually, It does matter, because we need to receive 2 different X inputs and write out another one. There we go. There. And take this guy like so. Ah! Look how nice and symmetric this all is, though. Wow, very nice. Okay, and then in here, we're just going to say test equal P0 ACK. If they are equal, that means the state of the button has not changed, so we shouldn't do anything. Instead, we'll only do things if they're not equal. Well, we could, I suppose, unconditionally at this point, move P0 into ACK. But if they're the same, we don't need to, so we can save a cycle power-wise by making the move conditional. Move P0 into ACK, and then we can test ACK again, making sure that we do so in a way that we only execute if it's minus. We want a plus result to mean we don't have to do anything. So what kind of test are we going to do then? Test equal ACK of so if it's 100, we don't need to do anything. No. If it's 0, we should not do anything. Don't send the score, right? Yeah. So if it wasn't 0, that means it did change recently, and it's now 100. So we need to send a 1 to x0. x1, I should say. And then we just sleep 1. And put the same thing here. Great. So let's test this guy real quick. Wow, they went through that first cycle real fast. They're both testing whether P0 is the same as ACK, and it is, so they do nothing. And then they sleep for 1, and again. And now they're testing whether it's the same as ACK. For that guy it is, so he does nothing. This guy says, oh, gotta start working. Puts 100 into ACK, tests whether ACK is 0. It wasn't, so someone must have just pushed the button. So he tries to send a 1, but this chip is checked out. Okay, so we have to, but I think it's good. I think we're in good shape here. So what I was about to say is that this poor guy here needs to sleep. He needs to block on 2 different inputs, and they might not each be sending each cycle, right? So my first solution was, oh, we'll just have them send each cycle regardless. And that might be the right solution, but it reminds me of the kind of wrong thinking I was doing before, right? Where I said everything's got to happen every cycle, all the endpoints need to be smart. So I want to see if there's a way that I can avoid that. And I think there is, which is just to wire them up to the same port, right? Yeah. They don't need to be different ports. Gosh, what have I done? Let's do this, and we learned that it's okay to write the same X input, X bus. Yeah. And now only the ones who actually need an update will send it. We'll just encode this as a -1 instead of a 1, and this guy will say his whole thing will be sleep X. No. Shoot. Because he needs to send every cycle, doesn't he? So he can't afford to be blocking for these guys who aren't sending anything. He needs to do something every cycle. It means he can't ever just block. Alright. But it can all still be 1 port, which is nice, I guess. Maybe? Does that actually help us anymore? It doesn't seem like it does. It doesn't make things more or less complicated, really. Yeah, I don't know. We'll make it the same port, why not? I don't know. I think it's more architecturally clean if they're different ports. So there you go. The architect has spoken. We just need to move 0 to x1. We have to make a dummy right here saying, yeah, go ahead and don't do anything. And this guy needs to just, every step, add x0, add x1, move ACK to x3, and sleep 1. I think that should do it. I don't remember, is this the exact same program I wrote last time? I do not recall. It seems like it ought to have been, but who knows. Okay, so this guy should now be waiting. Yes. These two have both decided to do nothing, so they're going to move a 0. Great. And we write out a 0. And we get a couple more zeros, and we write out a 0. Great. Now this time something more interesting will happen. This guy will send not a 0. Now here's an interesting thing. It is a little tiny bit different that they're on different ports, because it means we block for this guy first. So if this guy happens to be ready first, we're sort of wasting some time. But I don't think we're wasting any resources that actually matter in this game. We're executing the same number of instructions, just in a different order. So the power doesn't matter. I think it's fine. In a real circuit, though, if we had something that behaved this way, like, let's say these were network channels, it would be much better to be able to make progress on this guy who's ready, instead of waiting for this guy and then getting to this guy later. Here, it shouldn't matter. So he sends a 1, and we add a 1, and we add a 0, and we write the thing. Great. Okay. So how much of an improvement is this, anyway? I don't know. Over what we had. I guess we'll get to see the chart and compare, right? But it seems like it's better. Because I remember these guys were like basically full, weren't they? Or is it exactly the same? Did I write exactly the same thing? These lines didn't move at all. Return to email. Ah. No. This is better. We used a little less power because this one was doing some unnecessary logic in these guys. And this guy was doing a little bit more work as well. He was sleeping for each one of them instead of just unconditionally reading from them and then sleeping. Oh, and I actually did wire them both up to the same input. Who knew? I don't remember doing that. All right. Do we want to get involved with a design 3 that was using this guy right now? We're a little bit short on time, but I don't exactly want to do that next episode. I want to get to new puzzles next episode. I feel like we've been doing a lot of review recently as we unlock new powers. Like this whole episode was review, and I don't think the last episode was review, but it might have been. If so, I don't know. Sorry, I've done like an hour of puzzles you guys have already seen. But I think revisiting them with new tools is fun and interesting. So, like, if you guys don't like it, too bad. All right, what do we got here? Can we do this better? It seems like we ought to be able to, right? I'm not sure exactly how. Like, the solution that we're thinking of, like, the wiring diagram is very simple to draw, right? It's just like, oh, is it more aesthetically pleasing down here? It is not. I guess I can do something like that to make it look, it looks so dumb. Alright, whatever, it doesn't matter. Oh, also this is backward. There we go. It's like that, and then we want to do basically this. Like, that's the wiring diagram we want. And maybe this guy has to upgrade into a large chip. But maybe not. So I'm actually not sure we can do this with just one chip, because I don't know if we have enough state. We kind of need to store at least 2 registers worth of state, right? 1, which buttons were pushed last cycle, so that we know whether a new one has been pushed this cycle. And 2, what the score is. Obviously, we cannot allow the score. The score has to live in a register. It can't live on a pin or anything like that. How about what buttons were pushed? I think that has to live in a register too. And so what that means is we can't do any math to figure out, like, we can't do any math to, like, extract out a digit from this thing and check what it was. Like, what would be nice to do is to say, all right, let's just subtract the current button state from, well, subtract the past button state from the current button state. Maybe I should say old from new. Subtract the old button state from the new button state, and if the difference is 10, do add a point, and if the difference is 1, subtract a point. And like, ta-da! Oh, we can do that. Can't we? So I was working with this problem. All right, so first of all, let's throw this away. Oh, that's more symmetrical too. How nice. I was thinking about, like, the problem is that when we do the subtraction, we lose the value that was in the DAT register, right? But that's okay, because we can just read the new value again. We can read again. We can read from this X bus as many times as we want each cycle. It doesn't mind. So I think that these 2 registers should be enough. 1 to do math in, and 1 to store the score in. And in fact, we kind of need to do math on both of them, though, don't we? It's going to be a little bit awkward. We might run a bit shy of instruction counts, but maybe we can manage it. We have a lot, like 15 or something in here, I think. 15. I know that in a 2-wide there's 9, and I could count them here, but it seems like what we have is basically 5 times how many squares tall it is minus 1. So we should have 14, right? That makes sense. 1 for, like, the rounded edges basically is getting lost, and each of these are 5 instructions tall. Okay, so we have 14 instructions, which is quite a few, maybe not enough. But what we're going to do is the following. We're going to start by subtracting I kind of want to do the subtraction in reverse, right? I want to subtract ACK from the input, not subtract the input from ACK. But we don't actually have a way to do that. So we can just work with negative numbers the whole time and it'll be fine. So let's just sub x1. That's our first instruction. Great. And then now we need to test whether that value was either -10 or -1, indicating that something should happen. Test eq ACK -10. That means we should add a point. If so, move 1 to ACK, add that, move ACK to dat. And we have to be careful here with what we do to ACK here, and what tests we do to make sure we don't like end up scoring a point and a foul at the same time for some silly reason. And indeed, oh, we've lost the old state. It's gone. I see. Huh. Whoop. Just dropped our phone there. Bumped it off the table. And we have no way to get it back because we had to do math on the value that was in dat. Ah, that's not true. We do have a way to get it back if we want. We can, because we know we can read the value that's on this guy if we feel like it. And we know that if we add 10, we'll get back what we used to have. So that's a thing we can do. But actually, it occurs to me, we can just, we don't ever need to actually test anything if we've actually done this math, right? Because that means we determined a point had been scored. We don't need to check for a foul. I'm not sure the right way to skip over all this stuff, but let's just go ahead and say it's to put a plus here, or a minus, I should say. And now we'll test whether it's equal to, test whether ACK was equal to -1, in which case now we're in a sort of tricky spot. Let's just go ahead and be a little bit lazy here. I think we can avoid this jump instruction if we're a little bit more careful. But for now, let's jump to score. And down here in score, we're going to just move dat to x3 and sleep for 1. So I think we can actually do better. But okay, for now, let's finish up doing it this way. If it was equal to -1, then move -1 to ACK, add dat, and move ACK to dat. I'm not very happy with these repeated instructions. But this looks kind of okay, right? Anyway, what I was getting at is it seems to me like instead of this jump, we could instead I guess we don't even need the minus there, really, right? Whoa. Here's a crazy idea. What are the various values that could be the result of this subtraction? What if instead of comparing for -1 and comparing for minus... Like, so, basically, it can either be 0, the inputs are the same, don't do anything. Or it could be -1, meaning foul. Or it could be -10, meaning point. The problem is... I'm thinking we could use like a test compare against -1. And then thereby avoid doing a second test. I'm not sure that's really much of an improvement. At any rate, it seems like there might be something more clever we could do here, but I'm content with what we have for the moment if it actually works. Presumably it doesn't, but let's see what goes wrong. So what do? We subtract x1, the value of which is 0, and our ACK was 0 as well. So we test whether... oh, whoops! Missed something important here. Let's in score... Well, actually, this is fine. We'll have that be that. But before we sleep, we need to also move x1 into ACK, tracking what the state of the buttons was last turn. Oh, I gave it a... No, that's fine. I'm dumb. I'm dumb. That's all. Continuing on. Fine. So we write a 0. And we store the state, and we go to the next phase. And this all happens again, nothing interesting happens. Now what? We sub x1, so that should be -10, right? Yes. Was it -10? Yes. Move a 1 to the ACK. Add dat, the old score. And, move ACK to DAT, because we need to save the old score, and then jump. And now we write out the score, we save the old button state, which is now 10, and we go on. Sub the new button state is still 10, the difference is 0. Great. We didn't do anything. We just wrote out the old score, and now this time the button state is 0 again. So what's the difference in score? Why, this time it's +10. Don't do anything. Great. And we write out the thing, and now we get a difference in score that is -1. Right? Oh, -100. Woo! Alright, I had these upside down, I guess. There you go, whatever. Oh! Is this interesting? Alright, well, whatever. So, I think we're basically done at this point. Yeah, the scores are all right. And I think we could maybe even save just a little bit more power if we did only one comparison. And we compared it to -10. If it's greater than that, well, then, if it's less than that, it must be -100, in which case we can go ahead and score a foul. If it's less than that, don't do anything, i.e. jump straight to the scoring mechanism. And if it's equal to that, I'm not sure exactly how to use test compare to do that, because we'll save a comparison, but we'll eat a jump instead. Which doesn't seem like it's any kind of improvement, actually. All right, so I guess I'm happy with where we are. Which is good, because this has been actually a longer episode than I intended, just playing around with all the new toys. But I think we made some good progress on like learning new ways to apply the new tools we have, and to some of the old tools as well. Thinking about better ways to solve the same problems, which I think is what puzzle games and optimization challenges like this one are all about. So thanks for watching, and I'll see you next time.